Bismillahirrahmanirrahim. Assalamu alaikum. Let's continue our discussion on support vector machines. We gave you a quick overview of support vector machine classifier. We talked about hard SVM, soft SVM, and kernel trick. In hard SVM, we assume that the classes are linearly separable, and we want to find a hyperplane that separates the classes in the feature space such that no point in the training data is misclassified, or all the points in the training data are classified correctly. And then we talked about soft SVM, that allows us to misclassify some of the points while learning maximum margin classifier. And then we talked about the kernel trick, a very quick overview of the kernel trick. If we have classes that are not linearly separable, we project the feature space to higher dimensional feature space to make the classes linearly separable, and such that we can fit a separating hyperplane in the higher dimensional feature space to separate these classes, right? We take a step forward and we start exploring each of these topics in more detail. Start with hard SVM. In hard SVM, we quickly recall that we have a binary classification problem. For one class, the red here, the associated label is 1. For the blue class, we have the label -1. The classes are linearly separable, and we want to find out this hyperplane W transpose X minus theta is equal to 0 that separates these two classes in the feature space such that the classification margin is maximized. Right? Okay, let's mathematically formulate the notation. We again assume that we have n data points, and for each data point, the input has d features, x1, x2, and xt, right? That are indexed, that are contained in this vector x. For each data point, output can be -1 or 1. We have a binary classification problem. If you recall, we defined a perceptron classifier that is again hyperplane separating the classes, and that's how we defined the perceptron classifier. If the weighted sum of inputs is greater than theta, the output is 1. If the weighted sum of input is less than theta, the output is -1. And we could compactly express this as sine of inner product W transpose X minus theta, right? So that was a perceptron classifier, or that's separating hyperplane in the feature space, right? Support vector is the data point for each class closest to the hyperplane. So here we have two support vectors. So this red point is a support vector for class 1, and this blue point here is a support vector for class -1. We also define margin, the distance between the support vectors, right? So hang on, yeah. I have denoted with this row the classification margin, or the margin, the distance between the support vectors. The problem in hand is that we want to find a hyperplane for which this margin is maximized. And we know that this maximization depends on the support vectors. Other training data points are ignorable because this is the distance between the support vectors. So this dashed red boundary and this dashed blue boundary, the distance between these two boundaries is the classification margin, or the margin which we wish to maximize while finding W transpose X minus theta is equal to 0. We refer to this as hard SVM because we require all the training points to be classified correctly. We require all the red points to the right of this red boundary, and we require all the blue points to the left of this dashed blue boundary, right? That's why we refer to this version of SVM as hard SVM. We do not we do not require any misclassifications. We require all the points to be classified correctly by the separating hyperplane, right? Okay. Since the support vectors are equidistant from the decision boundary, we define two planes. W transpose x minus theta is equal to 1. We call it plus plane, and we call it minus plane. W transpose x minus theta is equal to minus 1. And these two planes, in fact, contain the support vectors. So this dashed red line is the plus plane, and this dashed blue line is the minus plane. And we note here that W is perpendicular to both the decision boundary and these planes, because these planes are perpendicular. These planes are parallel to the decision boundary. W transpose x minus theta is equal to 0, and therefore W is perpendicular. W is orthogonal to each of these three planes, right? Okay, we take x minus as any point on the minus plane. So it does not need to be the data point, right? For example, I can take this point as x minus. And next I take a x plus point on the plus plane that is closest to x minus. We can relate x minus, x plus, and W. Can you help me in relating these three? So W is perpendicular to both x minus and x plus. The distance from x minus to x plus would be that x plus you can reach x plus from x minus by moving in the direction of W. Or we can say x plus is simply x minus plus beta times W, right? Since the margin is the distance between plus and minus planes, we can find this distance using this relationship between x plus and x minus. So by definition, the margin is given by the Euclidean norm of x plus minus x minus, and that is given by beta times W, Euclidean norm of this vector, and that is given by beta times the Euclidean norm of the W, right? Okay, moving forward, we note that x plus is equal to x minus the beta W, and that's how we defined the plus and minus planes. And using these three, we obtain W transpose x plus minus theta. So instead of x plus, I will substitute it this here to obtain this formulation. And finally, I noted that W transpose x minus theta is equal to minus 1. And consequently, beta times W transpose W is equal to 2. Or I could write beta is equal to 2 over square of Euclidean norm. And we already shown that margin is equal to beta times Euclidean norm of W. And when we compare these two, we can determine margin as 2 over Euclidean norm of W. So we have expressed margin in terms of W, and now we can formulate optimization problem. We want to maximize this classification margin. This is equivalent to minimization of norm of W or square of norm of W. It's one and the same thing, right? If you minimize 1 over Euclidean norm, that is equivalent to maximizing Euclidean norm or square of Euclidean norm. And this can be interpreted as we want to minimize norm of the vector that is normal to the decision boundary hyperplane. So we're all set to define an optimization problem. We want to minimize square of equilibrium of W. At the same time, we do not want any misclassification. We require all the points to be classified correctly, right? It simply means we require every point xi for which the label is 1 to be on the right side of the plus plane, and we require every point xi for which label is -1 to the left side of the minus plane. And if I can combine these two conditions, I can write simply equivalent to, so I require yi times w transpose xi minus theta is greater than 1. We have seen this before when we studied perceptron classifier. We can combine these two conditions into this one single equivalent condition. Okay. So now we can define optimization problem. We want to minimize square of equilibrium norm of W, which is W transpose W, subject to these inequality constraints. And we have n number of inequality constraint, one inequality constraint for one data point. And we require every data point to be classified correctly. Right? Okay. So we have this optimization problem. How do we interpret this? We want to minimize norm of the normal vector, defining the separating hyperplane while ensuring all the tuning points, my apologies, are classified correctly. How do you see this problem? This is objective function is quadratic and it is convex, and inequality constraints are linear. This problem, or this type of optimization problem, is known as quadratic program. A quadratic objective function which you want to minimize, a convex function and subject to linear inequality constraints, is known as QP, a quadratic program. It has been studied very extensively in the literature, and there are very computationally efficient algorithms which you can employ to solve this optimization problem. The solution of this problem gives us a maximum margin classifier W transpose X minus theta is equal to 0. And for this maximum margin classifier, we know that classification, what is classification margin? Margin is 2 over equilibrium norm of W. We have an optimization problem here, which we can use to determine maximum margin classifier that separates the two classes in the feature space and such that the margin is maximized. And we can stop here, but I would like to introduce you to the concept of duality theory in optimization. So we will use the concept of duality theory from convex optimization to formulate the dual problem for this optimization problem, and that will help us in establishing usefulness of the kernel trick later in the course. Right? This is probably beyond the scope of this course, but this is something good to know. Okay, we start with the concept of the dual problem using Lagrange multipliers. If we have a convex optimization problem of this form, that we minimize objective function subject to m number of inequality constraints. This optimization problem is convex in nature, or is a convex optimization problem if the objective function and inequality constraint functions are convex in nature. If these functions are convex, the problem is a convex optimization problem. right? Okay, the duality theory states that for this problem, or we call this primal problem, we can formulate a dual problem, what we call Lagrange dual problem or Lagrangian dual problem, is this, that we maximize. Okay, let me explain this, right? So what's the objective function here? The objective function here is inside these parentheses, we have f naught, the objective function of the primal problem, plus weighted sum of inequality constraint functions. And for ith inequality constraint function, I have associated this alpha I. And this alpha I is called a Lagrange multiplier. Right? Okay, if you see this term here, this is objective function plus weighted sum of inequality constraints. Right? And we take infimum over theta. It simply means we're with respect to theta, we're minimizing f naught of theta plus weighted sum of inequality constraint functions. And we have a condition on these weights. We require each of this alpha I should be greater than or equal to 0. And when we take infimum, when we take minimum with respect to theta, the function we get here will be a function of these Lagrange multipliers, or alpha only. So this L of alpha is known as Lagrange dual function. So we have a primal problem up here. This is primal and this is dual. And the connection between these two problems is that under certain conditions, and those conditions are known as Slater's constraint qualification, if this holds, the optimal value is same for both the problems. Or in optimization theory, we say that the duality gap, the difference between the primal optimal value of the primal problem and the optimal value of the dual problem is equal to 0. Okay, now we formulate the dual problem for the optimization problem we have in SVM classifier. We want to minimize half W transpose W. In fact, we want to minimize square of equilibrium number of W. I have added this 1/2 here because we know that it's not going to change our optimization problem. And we require these constraints to be satisfied. We require all the points to be classified correctly, right? And we have n number of these constraints. For this optimization problem, we first formulate a Lagrangian that is simply incorporating the inequality constraint functions in the objective function, right? So we have objective function, right, plus weighted sum of inequality constraint functions, right? Okay. In standard form, we require this to be less than or equal to 0. Since we have greater than or equal to 0, so therefore, instead of positive sign here, we have added a negative sign here, right? I hope this is clear, right? So this is the Lagrange. This is the Lagrangian. So alpha high is the Lagrange multiplier that is associated with the ith constraint, ith inequality constraints. And to determine Lagrange dual function, we want to minimize this with respect to W and with respect to theta. And this is still a convex function of W, right? It's W transpose W. The quadratic term coefficient is positive, and this is still convex. And we know that if we take derivative of this with respect to W and the derivative with respect to theta, we can minimize this Lagrangian with respect to W and theta. Okay, let's take derivatives with respect to W and theta. So we have this formulation of Lagrangian, If we take derivative with respect to W, that's derivative gradient with respect to W, what you get is, so for this term you get, for W transpose W you get 2 times W, and because of half you only get W. And for this term here, so derivative is linear, you move derivative inside, so we have W transpose Xi, so you only get Xi left, you only left with Xi. This -1 would be gone and this theta would be gone, because there's no dependence on W on theta and 1. And eventually what we get is the partial derivative of Lagrangian with respect to W would be given by this. And when we substitute this equal to 0, we get W as alpha I, yi, xi. And this is a very remarkable result, and we will use it. We use it very frequently. And how do you interpret this? A normal vector W is a linear combination of the data points. And we will see very shortly that W is a linear combination of the support vectors only. In fact, we do not need all the data points to express W. Okay, partial derivative of Lagrangian with respect to theta. And when we equate it to 0, so this term would be gone, this term would be 0. Here, so this would be 0. We only get summation of alpha I, yi is equal to 0. And this is the partial derivative of Lagrangian with respect to theta equal to 0. Right? Okay, what was the objective? We wanted to minimize this Lagrangian with respect to W and theta. And we know this is a convex function of W and theta. We have computed gradient, we have computed derivatives. And when we substitute these, when we incorporate these in Lagrangian, we can get a minimum value of the Lagrangian with respect to theta and W. So let's combine these three. So if we combine these three, we obtain, okay, instead of W, I've substituted this here, and also here, right? And I have also used the fact that alpha I, yi, sum over all data points is equal to 0. Right? And if I incorporate, so this would be 0. So what's here is exactly this, but here we have 1/2, here we have -1. So when you combine these two, you get this quantity, which is coming here, and then we have my negative half of this term by combining the first two terms. Okay. And this is the Lagrange dual function. How do you interpret this function? Is this convex, concave, neither? Look at the quadratic term. We have x transpose xj. Okay, talk about alpha. It's the function of alpha. We have alpha I, alpha j. We have a quadratic effect here. Right? And this is a concave function because we have a negative sign here. We have minimized over W and theta, and now we have Lagrange dual function. If you recall the dual problem, in dual problem, we maximize the Lagrange dual function. And we're all set to define dual optimization problem. That is, we maximize Lagrange dual function subject to condition on the weights, the Lagrange multipliers. And I can say that this is a quadratic program again. because we are maximizing a concave function. This is equivalent to minimizing negative of this, which is a convex function, subject to linear inequality constraints. This is also a quadratic program. And when we solve this, it turns out that alpha I, these weights, are 0 when xi is not a support vector. So we have weight that is associated with each xi, each inequality constraint, each data point. So when we solve this, in fact, we can use what we call Karush, Cohen, Tucker, KKT conditions to prove that alpha I is equal to 0 when xi is not a support vector. Because the inequality constraint we had in the primal problem, that is equal to 0, or that constraint is active when for a support vector point. Right? Okay. So without going into more detail, we assume that alpha I is equal to 0 when xi is not a support vector. If we have this information, if we have some information about the support vectors, right, this can be used to reduce the complexity of the optimization problem, because we know that some of the Lagrange multipliers which we are trying to find are 0, or we do not need to incorporate those points in this summation here, right? We use support vector. Okay, I'm going to define this notation SV, a set of support vectors, the points in the feature space for which the Lagrange multiplier, the associated Lagrange multiplier is non-zero. Because we know that for only support vectors, alpha I is non-zero. For points that are not support vectors, alpha I is equal to 0. Right? Okay. Moving forward. So maximization of Lagrange dual function gives us alpha. And we know that most of the alphas are 0. Only the alphas that are associated with the support vectors are non-zero. Consequently, I can write W. So we had this formulation of W, which we obtained by taking derivative of Lagrangian with respect to W is equal to 0. And from there, we obtain this expression. Here we have summation from I is equal to 1 to n. And we know that most of the alpha i's are 0. So instead, I can take a summation only over a set of support vectors. So we have only used support vectors. So using this formulation, we can write the decision boundary as this. So what is the decision boundary? W transpose x minus eta is equal to 0. If I use this formulation of W in the decision boundary, I can obtain this. For any test point, we only need to compute the inner product of the test point with the support vectors, because this is my decision boundary. For any test point x, this is a test point. If I substitute test point here and it computes this, and if this turns out to be greater than 0, the label is 1. This is less than 0, minus 1. So we only need to compute the inner product of the test point with the support vectors only, using this CD formulation. And in fact, if you have not observed yet, we do not need to determine W explicitly. we only need to know support vectors and associated alpha I. If we know support vectors, this is the decision boundary, and using the same expression we can compute the label, we can estimate the label for a test point, right? So that was a formulation of a dual problem for the optimization problem we had for hard SVM. Yeah, as I said earlier, this is something good to know. You may not need to know as far the scope of this course is concerned, but this is something very useful, which we employ very frequently while carrying out optimization. Okay, let me conclude hard SVM. We formulated optimization problem to learn maximum margin classifier using the training data. And for the primal problem, we also formulated dual problem, and we saw that in using dual formulation, we only need to compute the inner product between the test point and the support vectors. Since the optimization problem constraints represent the misclassification on the training data, the error loss on the training data is 0. We require all the points to be classified correctly. And in fact, due to this characteristic of this SVM, we refer to this version of SVM as hard SVM or hard margin SVM. What are issues with hard SVM? It can overfit very easily and therefore cannot generalize. What do you mean by this? So due to outliers or erroneously labeled observations, optimization problem can be infeasible. Infeasible means the constraints are not satisfied. There is no separating hyperplane that classifies the points correctly. For example, consider this case. So only this single point, this blue point here. So this could be here due to erroneous label, or it could be an outlier, or it could be due to some noise in the measurement. But the presence of this single outlier, when you try to find SVM, hard SVM using optimization problem, the problem would be infeasible because the data is not linearly separable, and that was the first assumption we had. Or some of the outliers can influence the margin. For example, this red point, if this is blue label point, we could have a different SVM classifier. Or if this is here due to some noise, this point has influenced, this point has changed our classifier, and this also changed the margin of the classifier. So we can address these two issues by allowing the misclassification during the learning of the maximum margin classifier, and that version is referred to as soft SVM, which we will study in the next video. Okay, we stop here and we'll continue in the next video, inshallah. Allah Hafiz.